Alright folks, this is chapter 17, which is a lot like chapter 16. It's just additional aspects of aqueous equilibria. So we're doing Rice tables more, we're doing equilibria reactions, we're just throwing a couple more things at it. Nothing that's too difficult. If you have Rice tables under your belt, you're going to be fine in this chapter, hopefully. Alright. So the first thing we want to talk about is called the common ion effect. And we've already sort of talked about the common ion effect in that we showed the sulfuric acid, polyprotic acid equilibria reaction. So we sort of have an introduction to that already. But the common ion just means that if you have a solution that has an ion from another source, so maybe in this reaction we have acetic acid over here. Acetic acid and water produces H3O plus and acetate. Okay, if we were to throw in some, say, sodium acetate, NaCH3COO, sodium acetate, we're adding a source of acetate. Right? It didn't come from my equilibria, it just came from the sodium acetate salt. And so in the common ion effect, there's a shift in the position of an equilibrium based on the addition of a substance that provides that common ion with one of the ions already involved in the equilibria. So if we add sodium acetate to this reaction, according to the Chatelier's principle, we're going to have an excess of acetate, which is going to shift the equilibria away from that excess of acetic acid or of acetate, and so it's going to go in the reverse direction. We already know that from the Chatelier's principle as well. All right, so here's an example of a common ion effect reaction. We have a Rice table again. So I, C, and E here. And in the problem it says the pH of 0.1 molar acetic acid is 2.89. Calculate the pH of a solution that is prepared by dissolving 0.1 molar of acetic acid and 0.1 molar of sodium acetate in enough water to make 1 liter of solution. All right, so here again, we're going to make a total of 1 mole per 1 liter, so that's osmolarity. So if we think about the concentration of CH3COOH, that's just 1 mole per 1 liter, so that's, 0.1 mole. So that's 0.1 molar. Also, the concentration of acetate, we're told that it's 0.1 molar sodium acetate, so CH3COO minus is also 0.10 molar. We don't really care about the sodium. The sodium is not involved in my equilibria, so again, I'm just looking for that species that is involved. And so in sodium acetate, it's just the acetate, not the sodium. Okay, it's just a counter ion. All right, so then I go to my Rice table, and initially I put in 0.10 molar, put in effectively 0 here, and again 0.10 molar. Okay, the change, here's where we're going to put negative x again, just like before. I'm going to put positive x here and positive x here. Okay, so at equilibrium then we have what we initially had, 0.10 minus x, x, and 0.10 plus x. Alright, so far the only difference is that we started with some acetate here in my Rice table. Okay, so now we are given a Ka for this acid, and so we set up our equilibria expression, which is Ka is equal to concentration of products, H3O plus, CH3COO minus acetate over concentration of CH3COOH acetic acid. Okay, we go to my Rice table and we put in our values. Okay, so we have here concentration of H3O plus is X. The concentration of acetate is now what we had initially plus X, the additional amount, and we divide it by 0.10 minus X. All of this equals 1.8 times 10 to the minus 5. All right, again, we're going to do the same thing as before. We're going to make an assumption. And if we make an assumption that x is small, this becomes x times 0.10 over 0.10. Everyone follow? If we have $1 million and we add a penny to it or we subtract a penny, it doesn't really matter. It's still small, or still $1 million. X was small. And so here, when you do that, these cancel out, and x just equals 1.8 times 10 to the minus 5, which is a good assumption. So our assumption passes here. X is that. And now if we want the pH, pH is negative log of H3O plus, which is X. So negative log of 1.8 times 10 to the minus 5. The pH is 4.74. All right, so that's common ion effect. If you look here at common ion effect, it's really just Le Chatelier's principle again, right? So we add acetate, we're perturbing the system by adding some acetate. That extra acetate is going to shift the reaction in the reverse direction. It's going to suppress the dissociation of acetic acid. All right, here's another example problem. Calculate the concentration of all species present, the pH, and the percent ionization of HCN in a solution that is 0.025 molar HCN and 0.01 molar sodium cyanide. Okay, so here again, we want to think about our reaction of interest. So we're going to write our R reaction. And this is where people get confused, I think, a lot of the time. So our Ka that is given in the problem is an acid for HCN. So that is really going to be our reaction of interest here. So we have HCN. We know it's a weak acid because we're given a Ka. So when this is with water, we get an equilibrium reaction, which produces a proton donor. So we get H3O plus Cn minus. Okay, now we're going to fill out the rest of our rice table here. Right, so initially, for HCN we're told it's 0.025 molar. And for water, we don't really care. For H3O plus, it's effectively 0. And cyanide, here's where it gets interesting. So we don't have 0 of cyanide. We have sodium cyanide. So again, we want to look at this additional species that's going to affect our equilibria. Sodium, not in our reaction of interest. Only cyanide is. So we really are only concerned about the cyanide. And here we have 0.01 molar sodium cyanide, so we also have 0.010 molar of cyanide. Okay, again, the chain is minus X, plus X, plus X. At equilibrium, we have 0.025 minus X. We have X, and we have 0.010 plus X. All right, so now that we have our rice table, we want to think about our Ka expression. Okay, our Ka is products, H3O plus, Cn minus, over HCN. Okay, we start plugging in values here. We get X, 0.10 plus X, and 0.025 minus X. We're going to make an assumption. Assumption is that X is small, so now we have 0.10 times X over 0.025. And we're going to simplify this, solve for X. X ends up equaling 1.2 times 10 to the negative 9. Okay, so that is a very small number compared to my original 0.01 and 0.025. So my assumption was very good. X is also my concentration of H3O plus. So if we find all the concentrations of all the species present, so we're going to have H3O plus in my rice table at equilibrium is just X, which is 1.2 times 10 to the minus 9. Okay, I'm going to have HCN, which was 0.025 minus X. Okay, so if we put X in here, we're going to take 0.025 and we're going to subtract out 1.2 times 10 to the minus 9, which is going to give me effectively, again, 0.025. It didn't change it, right? Because that's the assumption, is that it doesn't significantly change the value if we subtract or add x. So it's kind of the same again. All right, and then for Cn minus, the other one we care about, cyanide, it's 0.010 plus x, which again is effectively just 0.010. All right, the only other one is hydroxide. So if we have hydroxide, we have Kw divided by H3O plus. Hydroxide is going to be one times 10 to the negative 14 divided by 1.2 times 10 to the minus 9. This is 8.3 times 10 to the minus 6. Oops, sorry. And then the last thing it asked for was the pH. So again, pH, negative log of H3O plus, which is x. So negative log of 1.2 times 10 to the minus 9. pH equals 8.92, so we're basic. And it also, go back, it says percent ionization here, so we got to figure out percent ionization. So that means of the HCN that we added, how much of it is cyanide. So for percent ionization, we want the amount of Cn minus from the acid divided by the amount of HCN originally. Okay, so that the amount that formed from HCN is just x. So we really want x divided by the original concentration, 0.025, times 100%. Sorry about that. So x was 1.2 times 10 to the minus 9 over 0.025 times 100. The percent that's dissociated is really, really tiny. It's going to be 4.8 times 10 to the minus 6%. So it's really small. Almost none of it is actually dissociating to form cyanide on the other side, but enough of it to give us a slight amount of H3O plus, so that we have more OH minus. We're in a basic range, and our pH is basic. All right. So next concept is buffers. Buffers are really, really important. Okay, so if there's one thing that my biologist friends pull out of this class and take with you to your biology degree, it should be buffers. Buffers are solutions that resist changes to pH, and for biology happens at very specific pHs. Okay, and so I have a picture here of a protein structure. This is protein structure of hemoglobin, and hemoglobin has this iron heme center, which you can, if you zoom into this, you can see here. It's got a central core porphyrin ring of these nitrogen atoms surrounding iron in the center. So each nitrogen has a lone pair. It can donate to an iron in the center. And hemoglobin, you know what it does. It absorbs oxygen and transports oxygen in the body. For hemoglobin to attract oxygen and bind to oxygen, it's pH specific. So physiological pH is 7.4. Okay, and when you exercise, your body produces lactic acid. So your blood pumps to your muscle, where your muscle is deficient of oxygen, needs oxygen, and lactic acid buildup drops the pH. So there's also a pressure change, but the pH drops just slightly to 7.2, and by lowering the pH to 7.2 with lactic acid, the affinity of this heme group to bind oxygen is decreased, and then it releases the oxygen to the muscle where it's needed. And this is called the Bohr effect. It's not after Niels Bohr, it's after Christian Bohr, but it's based on the pH and the partial pressure. So if the body system was not buffered at physiological pH, you'd have oxygen popping on and off every time it encountered an acid. And so blood is buffered, and many protein reactions happen in buffered solutions because the pH has to be tightly controlled. Okay, so this is sort of the motivation for why we need buffers. What is a buffer? So a buffer is just a solution that resists change to pH, and it does that by having a combination of a weak acid and a weak conjugate base in the same system. So think of it like a common ion solution where you have both maybe acetic acid and acetate. Okay, so that's one of the examples listed here. We've got acetic acid acetate buffer, we've got fluoride buffers, we have ammonia buffers, phosphate buffers. All of these are examples of different buffers where you have a combination of a weak acid in the red and its conjugate weak base differing by a single proton in the blue. All right, so if we think about a buffer system, here's the classic buffer of acetic acid buffer. We've got acetic acid on one side, CH3CO2H, and it can donate a proton to become acetic acetate and H0 plus on the other side. And if we introduce acetate from some other salt, so like sodium acetate or potassium acetate, then we have a common ion solution that contains both. So if we think about a solution that has both, if we add a base to this buffer, the base here, the hydroxide, we add a strong base to it, the hydroxide is going to look for an acid. And the acid is the weak acid, acetic acid. This strong, weak reaction is a 100% reaction. So again, this is not equilibria, this is just stoichiometry. 100% of it's neutralized to the conjugate, which is acetate. Okay, so acetate here is the weak conjugate base of acetic acid. If you were to add a strong acid, H0 plus, to this solution, it's going to look for a base. So again, we have a combination of both. So it finds the acetate here. Acetate plus the strong acid, we get a 100% neutralization reaction to produce water and acetic acid, the conjugate of acetate. So in both cases, if we add a strong base, hydroxide, we end up with a weak base, acetate. And if we add a strong acid, H0 plus, we end up with a weak acid, acetic acid. So this is the function of a buffer. It converts a strong acid or a base, OH minus or H0 plus, to a weak conjugate by a neutralization reaction. All right, so let's look at some buffer calculations here. Determine the pH of a buffer at equilibrium. Okay, so here is an example. Again, remember these boxes kind of tell you what we're doing. We're going to make a 0.1 molar acetate buffer, and this is from slide 11. We already did this, right? We had 0.1 minus x here, and we had 0.10 plus x here, and we calculated the pH. We solved for x. X was 1.8 to the minus 5, and the pH was 4.74. So we already did this. Go back to slide 11 and look at this. We had a combination of sodium acetate and acetic acid, both at 0.1 molar, and the pH was just 4.74. Okay, because x was equal to Ka in that case, we solved for x, and x was equal to Ka. If we take the negative log, okay, x is also equal to H0 plus, is equal to Ka. If we take the negative log of both sides, we get negative log of H0 plus, and we get negative log of the Ka. So another way to think about this is that the pH, negative log of H0 plus, is equal to the negative log of Ka, the pKa. Okay, so where we have equal concentrations of the conjugate acid and base, the weak conjugate acid and weak conjugate base in a buffer, the pH equals the pKa. All right, so let's go and determine the pH of this buffer on addition of adding a base. So we're going to add a base to this buffer. The buffer is going to neutralize that strong base, and we're going to get a neutralization reaction first. All right, so here we're adding 0.01 moles of solid sodium hydroxide to 1 liter of the buffer. We're going to make an assumption here. We're going to assume that there's no volume change. So we're going to add some base here, but it's not going to change the volume. All right, so here again, this is really key here. We're adding a strong base. So when you add a strong base, it's not equilibria. We have a single-headed arrow here. It's a neutralization reaction, so keep that in mind. So it's going to look a lot like a Rice table, but this is actually what we call a BCA table. A B, a C, and an A. Okay, in a BCA table, the B stands for before neutralization. So this is before. This is change. And this is after neutralization. So the other difference in a BCA table is you want to use moles. Okay, so BCA, just to reiterate, BCA equals single arrow, and we have a strong. Okay, we're not at equilibria anymore, and we use moles, not molarity. Okay, so these are the differences between BCA and Rice reactions. So here we have 0.01 molar of a buffer from the previous slide, and we have 1 liter of it. So therefore we have 0.1 moles of acetic acid. We added to it 0.01 moles. And we also had 0.1 molar sodium acetate, so we had 0.10 moles of acetate as well. All right, so if this is a 100% reaction, what's going to happen? We have a 1-to-1 to 1-to-1 reaction here, and we have 0.1 moles of acetic acid and 0.01 moles of hydroxide here, a strong base. So just like before in 1211, one of these is going to run out. We have a limiting reagent problem. Okay, so the limiting reagent here is going to be which one? Which one's going to run out first? Okay, it's going to be the base, right? Hydroxide is going to be limiting here. We have less of it than we have of the acetic acid here. So the change is going to be 100% until we run out of one of the reactants. So 100% until we run out is the limiting reagent amount, 0.01 moles. So we're going to subtract out 0.01 from this side, and we're going to add in plus 0.01 moles to this side. Okay, then after neutralization then, we ran out of the hydroxide. So now we have 0.09 when we subtract 0.1. Here we have 0 because we used it all. And here we have 0.11. We added it in. All right. So now when we want to think about the H3O plus, we have the Ka expression. We're going to solve the Ka expression for H3O plus. So that means we have Ka times acetic acid over acetate. And we plug these values in and from our BCA table. Okay, and we get Ka 1.8 times 10 to the negative 5 equals, okay, again we have 1 liter of solution, so we have 0.09 moles of acetic acid divided by 1 liter, so we have concentration of 0.09 molar, and we have a concentration of 0.11 molar. And this is not an equal sign, sorry. This is a multiply by sign. All right, so we calculate H3O plus concentration. When we do this calculation, we get 1.5 times 10 to the minus 5 molar for H3O plus. All right, so then if we take the negative log of that, pH equals negative log of 1.5 times 10 to the minus 5, that's negative log of the H3O plus, we get 4.82. So we added a strong base to our buffer, and what happened to the pH? All right, let's go back and look. So on the previous slide, the pH was 4.74. Okay, so we were slightly more acidic at 4.74. When we added some strong base to the solution, it only went up to 4.82. Right? The pH didn't change by much. That means the buffer worked. That's what we're looking for. We want the pH to stay close to the original pH, 4.74. All right, let's go on then. Let's determine the pH of the solution if you added an acid. Okay, so we're doing the exact same thing here, only now we're adding a strong acid, H3O plus. So when we add H3O plus, it's going to look for a base. That's my acetate. We put in our number of moles here. Okay. Here we're adding 0.03 moles of HCl. And again, we're going to assume that the volume doesn't change. Okay. And so here again, we look at which one is limiting. So here's my BCA table again. Before, change, after. I put in my original amount of acetate, I put in my original amount of acetic acid, and I put in how much H2O plus I'm adding. And again, remember that because I have a strong, this is a 100% reaction. It's not equilibrium, so there's no Rice table involved here. All right, so I look here, and I'm going to figure out which one's going to be the limiting reagent. So between these two, H2O plus and acetic acetate, which one's limiting? All right, H2O plus is limiting. So we got to subtract that one. So we subtract out till we fully utilize it all. And then we add it to this side. So now we have 0.10 minus 0.03, which is 0.07. I'll just write that, sorry. And here, all of it went away, so it's 0. And here we have 0.1 plus 0.03, so 0.13. Again, these are all moles. Keep that in mind, moles. All right, and we want to know what is the pH. So again, we are going to calculate the H2O plus concentration. So we've solved the Ka expression for H2O plus, and we're going to plug in what we know here. So we know that the Ka is the same Ka as before, 1.8 times 10 to the minus 5 equals, sorry, not equals, times the concentration of acetic acid. Well, that's on the right-hand side this time. It's 0.13 molar. Again, we divided by 1 liter here, keep that in mind. And 0.07 molar. We calculate this. This is 3.34 times 10 to the negative 5. Okay, that is equal to H3O plus concentration after neutralization, negative log of H3O plus is the pH. So pH is 4.48. So did the buffer work? Yeah. So again, we started, go back a couple slides, we started at a pH of 4.74. We added some strong acid to it, in the case of this slide, on 10, and when we added a strong acid, it only changed the pH slightly down to 4.48. All right, so this gets us to the Henderson-Hasselbalch equation. Okay, so before, what we did is we took a Ka expression, which was H2O plus the base over the acid, and we were solving it for H2O plus. That's what we were doing on the last two slides. That equaled the Ka times the concentration of acid over base when you rearrange this algebraically. All right, so if we then take this formula that we've been using, and let's say we take the negative log of both sides. So first, let's take negative log of both sides. Okay, when we do that, negative log of H2O plus is on the left-hand side, and we get negative log of Ka times concentration of acid over concentration of base. Okay, here. We can use log rules, and we can separate these two terms. So this is concentration of Ka times the acid to base ratio, and we can use log rules to separate this out. We know that negative log of H2O plus is just pH. So now we have pH equals negative log of the Ka minus log of acid over base. And we can use another log rule that says if you change the sign, okay, so we have a negative log here of acid over base, we can just change the sign And this now equals pH equals negative log of Ka plus log of base over acid. So by just inverting this, we change the sign out in front of the negative log to a positive. All right, and we want to take a look at this reaction, or this formula. Now we have pH, negative log of Ka, that's a pKa, plus log of base, concentration of base over concentration of acid. This form of the formula is called a Henderson-Hasselbalch equation. And we use Henderson-Hasselbalch. Here it is in the box. You don't have to know how to derive it, but you just have to know how to use it. This is really, really useful for buffers. Okay, so if we're in a buffer, the pH of a buffer equals the pKa of that buffer, the acid for that buffer, plus the log of the concentration of base over acid, so the ratio of base to acid. It's basically what we did up here on slide 10 and 9, just a shortcut way without having to do any kind of rice tables. So this just is a way to avoid rice tables. It's a shortcut for a rice table. All right, we can use Henderson-Hasselbalch in a number of different ways. We can use it to determine how to make a buffer of a certain pH. So we pick a weak acid with a pKa near, right? So if it's related to the pKa, we want a pKa that's close to the one we want, and then we adjust the amount of base or acid we have to get our ratio perfect so that we get the pH that we want. We can calculate the pH of a specific buffer, like we were doing before, or you could even calculate the percent ionization of a weak acid. All right, let's do some of those. Some example problems here. Determine the percent ionization of a weak acid. Okay, so we're going to do the third one. We've got glycine here. Glycine, amino acid glycine. Here's its ball and stick structure, and here's its molecular structure. It's got a positive charge on it. In the presence of water, it can donate a proton and make H3O plus here. So it's acting as a weak acid. We have a Ka given. It's a very weak acid. And we also have a pKa calculated for us. And we're told that we have a pH of 11.60. We want to know what is the percent ionization, percent dissociation, sorry. How much of this guy is over on this side? All right, so we're going to use Henderson-Hasselbalch because we have a combination of the two. And so we have pH equals pKa plus log of base over acid. All right, so we know our pH. Our pH was given as 11.60. We're given a pKa, that's 9.60, and we could solve for the log of base to acid ratio. All right, so here we just subtract 9.60 from both sides. And the difference is 2, so 2.00 equals now log of base to acid. All right, if we get rid of the log, we just do an anti-log. It's not negative log this time, so we just have 10 to the 2 equals base over acid. And 10 to the 2 is 100. So in other words, this equals 100 equals ratio of base to acid. So in other words, that's 100 over 1. So there's 100 in the base form for every 1 in the acid form. So if we look up here to this formula, which is the acid and which is the base? We have glycine with the proton and glycine without the proton. So this would be the acid form. They differ by 1 proton. This one has the proton. This one doesn't. This is the base form. And so at a pH of 11.60, we have 100 in the base form for every 1 that's in the acid form. Okay. So we're almost all dissociated into the base form here. Hardly any, only 1 out of 100 is in the acid form. And if you look at the Henderson-Hasselbalch equation, what you'll notice is that if you have a pKa plus 2, so we were plus 2 of the pKa, 99% is dissociated. So in other words, if we wanted to calculate the percent dissociation here, we would have 100 out of 101 total times 100%. This is 99% dissociated, or 99% in the base form, or 99% on the product side. If you have pH equals a pKa, then these two are equal to each other, and when you subtract them, you get 0. Okay, and so here you have 50-50. And if you have pKa minus 1, you have 9%. If you have pKa plus 1, you would have 91% dissociated, and so on. So you can see some patterns here. You don't have to memorize this. You can just calculate it in the same way we did over here if you like that better. All right, one more example of Henderson-Hasselbalch and we'll stop. Use Henderson-Hasselbalch equation to calculate the pH of a buffer solution prepared by mixing equal volumes of 0.2 molar sodium bicarbonate and 0.1 molar sodium carbonate. So again here, we've got the commonality here, which is CO3 2 minus and HCO3, so these differ by 1 proton. Sodium is just a counterion to get my charged species into solution. And so now we got to think about these two HCO3 minus and CO3 2 minus. Alright, so these differ by a single proton. The one with the proton is going to be the acid, and this one is going to be the base. Okay, we're told the Ka for this. The Ka here is 5.6 10 to the minus 11. This is really the Ka2, if we're getting technical about it. And so what we're going to use is Henderson-Hasselbalch. We know we have a combination of a weak acid and a weak conjugate base. So we're going to use Henderson-Hasselbalch here. pH equals pKa plus log of the concentration of base over the concentration of acid. All right, so pH, that's what we want to calculate. We don't know that yet. We do know the Ka. So if we find the negative log of the Ka, we should get the pKa, pKa2 here, which is going to be equal to 10.25. So negative log of 5.6 10 to the minus 11 is 10.25. So we plug that in here for the pKa plus log of base. So now again we said the base was the CO3 2 minus, and we had 0.10 molar for that one, and we had sodium bicarbonate as 0.20 molar here. And so here, if we think about this correction factor, we have more acid than we have base. So where should it be in terms of the pKa? If the pKa is 50-50, but we're not 50-50, then we should be more acidic. We have more acid than we have base. So we expect our pH to be below 10.25. When we calculate this with the correction factor in here, we end up with 9.95 for a pH. So it's lower than the pKa, which makes sense for us. All right, we will come back and do some more example problems of this. If you have any questions, please write them down now while you're watching the video. I will be back on Thursday. I can help you in office hours on Thursday or Friday morning. If you need me, you can email me. Otherwise, we will pick up here with your questions on Tuesday, so please have those ready. Hope you had a nice spring break.